two blocks of mass 10 kilograms and 8 kilograms respectively are connected by a light inextensible string. The blocks are accelerating up a rough slope which is inclined at an angle of 30 degrees to the horizontal. The force causing the acceleration has a magnitude of 250 newtons and acts on the 8 kilogram block in the direction parallel to the slope. The coefficient of friction between each block and the slope is 0.4. A. Draw a force diagram showing the forces acting on each block. B. Find the acceleration of the system. C. Find the tension in the string connecting the two blocks. Okay, so the first step is to draw a force diagram. So we'll just start with the 10 kilogram block. We'll introduce an I and a J system. For the 10 kilogram block, we have the weight acting downwards, which is 10 newtons, and then we will have a normal reaction, which we'll call R1. We have to have two different normal reactions, okay, because these will be different for each block. So we'll call this one R1, and then we have the frictional force acting downwards because as the block is moving up the slope. We're going to call that mu times R1, which is how we find friction. And then we'll have the tension in the string attached to the 8 kilogram block. Now for the 8 kilogram block, we will have 8 newtons acting downwards. We will have a different normal reaction to this one here, so we'll call that R2. We will have the frictional force on that one, mu R2, and we have a tension acting in this direction on the 8 kilogram block. And of course we have the 250 Newton force, which was already drawn on for us. Okay, so now trying to find the acceleration, what we need to do is treat the system as one object. So drawing a diagram for that, 8 kilogram block, we have 18 newtons acting downwards. We have a normal reaction, we're just going to call that R, and that mu times R will be the frictional force, and we have a 250 Newton force pulling it up the slope. So it will reduce the I and J system. So resolving in the J direction, so this direction, we have R acting upwards, and then downwards we have to split this weight into its components of 30 degrees. So we're going to have this component here, which is 18g cos 30. So it's minus 18g cos 30. And because it's in equilibrium, it's equal to 0. So that gives that R is 18g cos 30. Then mu R, so mu was 0.4 in the question, is 0.4 times 18g cos 30, which is 7.2g cos 30 degrees. Now it's resolving in the I direction, so this way. So we've got 250 newtons minus the mu R, so that's going to be 7.2 g cos 30 from the previous part, minus this component of the weight, which is 18g sine 30, and that's going to be equal to the mass, which is 18 times the acceleration A that we're trying to find. So in order to find A, we will need to, this is using Newton's second law. So A will be all of this, so 250 minus 7.2 g cos 30 minus 18g sine 30, all divided by 18. Use the fraction button on your calculator. Make sure you don't miss out any g's. It's quite easy to miss out a g when doing this sort of thing. And then we're going to get an acceleration of 5.594 meters per second. Now store this value in your memory of your calculator, but obviously we give the final answer here to 5.59 meters per second squared, correct to 3 significant figures. But this value we store in our calculator to use it in later part. Right, in order to find the tension, we just need to consider using one of the blocks. So I'm going to use a 10 kilogram block. We know that A is 5.594. So the forces here are 10g R1, mu R1, and the tension acting that way. And again, we've got an I and a J. So if we resolve in the I direction, we're going to get R minus the component of the weight here, which is going to be 10g cos 30. And therefore R1 is going to be 10g cos 30 And then mu r1 will be 0.410g cos 30, which is going to be 4g cos 30. Again, be careful not to miss out a g. Resolving in this direction, in the I direction, we're going to get t minus 4g cos 30 minus this component of the weight, which is 10g sine 30, minus, that's going to be equal to 10 times my value of my acceleration I calculated up here. Right, so rearranging this one's quite easy to rearrange, so that's going to be 10 times 5.594 plus 4g cos 30 plus 10g sine 30. Again, put it in my calculator, make sure I don't miss out any g's in the calculation, and then use the memory recall for that one. You give you 138.8 newtons recurring, and therefore rounded to 3 so it figures as 139 newtons. Now that's the end of the question, but we can verify this value is correct by just checking the other block. So if we check the 8 kilogram block, do exactly the same thing. 8g newtons, r2, mu r2, and tension acting this way, and the original 250 newton force acting this way. I and j. So resolving in the j direction again, we're going to get that r2 is going to be the this component of the weight, which is going to be 8g cos 30 is equal to 0. R2 will be equal to 8g cos 30. Then mu R2 will be 0.4 times 8g cos 30, which gives you 3.2g cos 30. Resolving in the I direction now, so we're going to have 250 going that way, but going against it, we're going to have mu R2, which is going to be 3.2g cos 30, minus this component of the weight, which is 8g sine 30, minus 8g sine 30, minus t is equal to mass times acceleration, so it's 8 times our acceleration. Now rearranging this is a little bit more difficult, but if we write out this bit here first, and then we take 8 times 5.594, that will be, and take the t over here, that will be equal to t. And if you put that in a calculator, making sure you don't miss out any of the g's, and using the value in the memory for this one, you're going to get exactly the same one, so 138.8 newtons, which is 139 newtons, which is the same as before. So this should be, the two parts should be the same. This is what we expected. Okay, this has been a video to show you how to resolve a connected object accelerating up a rough slope. I hope you understood, and I thank you very much for watching.